Okay, so in this video, I'm going to go through some of the extra recommended problems that were listed at the bottom of the book chapter problems on the handout posted at Canvas. Um, in this problem, we see that we have to try to turn a methyl ester into an amide. So one of the first things we want to do is look at how many carbons we have and if we can try to map the starting material onto the product. So if we look at the starting material, we see that we have 1, 2, 3, 4 carbons, and that maps on nicely to the 4 carbons that is in the product. So this means that one of our eventual goals will be turning this highly oxidized methyl ester into a reduced amine, because we see we need to have these 2 hydrogens added on here. Additionally, the other thing that adds on is this benzoate group. This can be done pretty easily by breaking this bond and just doing an amide bond formation with something like DCC. So our main target becomes trying to make this primary amine so that we can combine it with benzoic acid, or for this type of problem, you could say that you use benzoyl chloride and do a DCC coupling. So for making an amide, we don't need any DMAP. If you added it in, it never could hurt. So one way to approach this, and there's a number of solutions that are viable, will be to first reduce this all the way down to a lower oxidation state. So we can reduce this to a primary alcohol by reducing it with lithium aluminum hydride, followed by an aqueous workup. And now, actually, we have a couple different methods to go from an alcohol to a primary amine. One could be to oxidize this with PCC. This will give us to an aldehyde oxidation state. And then we could do something like adding in an excess of ammonia along with sodium cyanoborohydride. Oops. One too many hydrides on the borohydride, along with a catalytic amount of acetic acid to promote the formation of the amine intermediate. Alternatively, if you're worried about maybe having over-reductive amination problems, we could first turn this into an oxime. So this is essentially a reductive amination, only we are going to fully form the oxime first, then reduce this with sodium, metal, and ethanol. And there are yet more different alternatives here. So if we first convert this with PBr3 to the alkyl bromide, this can be displaced with sodium azide in an SN2 reaction. And then reduced with lithium aluminum hydride, or you can hydrogenate it with platinum oxide and hydrogen gas. And yet one more potential solution that I'll draw out, as we always have so many different choices here. It never hurts to review different ways to make primary amines. Would be do an SN2 reaction with phthalimide. This gives us our protected primary amine, which then can be also taken to the primary amine after reacting with hydrazine. So I think that covers most of the methods we have to go make primary amines, though potentially the shortest might be this avenue where actually the fastest way would be going directly here with Dibol. That would end up being the fastest. But any of these methods can work. Um, if you choose to do an over-reduction followed by PCC, that is more than adequate for what we're trying to accomplish right now. All right, let's look at an... Oh, I skipped a problem. Looks like I flipped these around. Well, hopefully you don't mind in the video. So we have a very similar problem here. And once again, we're going to try to map out where does the starting material kind of fit on the product. So here we can see we have 1, 2, 3, 4 carbons in the starting material. But now we have 1, 2, 3 carbon chain over here. So that means that somewhere along the way we're going to be trying to remove one of these carbons. And this is usually a sign for the Curtius rearrangement. So the Curtius rearrangement is the rearrangement of a acyl azide. So we're going to be trying to get this molecule to an acyl azide. To do this, first we can hydrolyze it using like lithium hydroxide. Then we'll do an aqueous workup. This can give us a carboxylic acid. Reaction of the carboxylic acid with thionyl chloride, SOCl2, convert to the acid chloride. And then sodium azide in heat will let us do that key nitrogen migration that now moves our carbon here. If we continue to, even in the same reaction, add water and heat this up too, we will get out a primary amine. So now we need to turn this primary amine into a secondary amine. That means we need to make this bond right here. So it's tempting to try to do an alkylation with benzyl bromide, but that always has over-alkylation problems. So what we want to do is do this all in one step with reductive amination. So in practice, you may first condense the aldehyde with the amine to make the imine, or many times you can get away with doing this all at once in one pot. Once again, we're going to have sodium borohydride and a catalytic amount of acetic acid to help assist the imine condensation and also provide the aminium that's needed to reduce with sodium cyanoborohydride. This one has slightly fewer options for how you could solve it. Alternatively, you could be trying to make an amide from this nitrogen then reduce with lithium aluminum hydride. That would also be, I'll draw that out just for comparison. So it would end up being one more step, but also effective. You'd probably have some base like pyridine around. Then reducing this with lithium aluminum hydride, followed by an aqueous workup, will give us the same product. All right, now we'll go back down to this problem. So now once again, we're trying to map out how in the world do we see this starting material in the product. So there's a couple things we can recognize. Somewhere we have to break open this 5-membered ring. Clearly somehow we're getting a nitrogen inserted into it. And that means that most likely these 5 carbons here are these 5 carbons here. This means along the way we do have some extra reductions going on. We've gone down an oxidation state. And we're also making new carbon-nitrogen bonds at the same time. So this is a signal for potentially using reductive amination. So if we were to try to do a reductive amination disconnection on this molecule, let me just erase all these extra things. What we do is break one of these bonds, and then turn the carbon into a carbonyl. So if we do this once, we see we'd get to this aminoaldehyde, and this would be able to do an intermolecular condensation for reductive amination. So this would directly go to the product using sodium cyanoborohydride and a catalytic amount of acetic acid. But the other thing we can take advantage of is that this bond could also be made through reductive amination. So that means that we could actually go back another step and look what happens when we break this bond. This ends up being an aldehyde. This also now is turned into the carbonyl, which is an aldehyde. And that means both of these steps could be performed at the same time, simply by reacting this with methylamine and sodium cyanoborohydride. So this would now just be an intermediate along the way. I'll move this structure over a little bit to give us more space. So this would just be an intermediate that's not isolated. It would directly keep going. And now we've really simplified our problem on the other side too, because in order to go from this cyclopentene to this bisaldehyde, we can use ozonolysis followed by a reductive workup with dimethyl sulfide. That'll directly break this double bond and give us two aldehydes on the other side. And now we have one final problem. This one in some ways is a bit more straightforward. We see that we have this starting amine. It's pretty clear that this 4-carbon chain ends up being this 4-carbon chain shown here. Potentially we could introduce both these with just reductive amination techniques. That'd be a pretty safe way to go. For any of these, you could also be doing an acylation to make an amide bond followed by reduction. So let's look at the amide bond followed by reduction, since we've used reductive amination quite a bit in the previous problems. So in this case, we could take this amine. Let's say we reacted it with benzoic acid and DCC. This makes a new amide bond. And then we can reduce this with lithium aluminum hydride followed by a water workup. To introduce this last group, we can now switch back over to the reductive amination technique using acetaldehyde, again, sodium cyanoborohydride, and catalytic acetic acid. Again, you could have actually done this all in one step just using reductive amination by using benzaldehyde and sodium cyanoborohydride. But just to reinforce that there's more than one way to do many of these different problems.